Before I start, I just want to quickly mention some of you who haven't heard me before might be wondering how how my voice fits to my name. I'm transgender. The whole world thought I was a guy, and at some point I realized that didn't fit, so I changed it. Anyway, science. I'm going to talk about a specific non-local isoperimetric problem. And I'm going to show that, I'm going to show that in a certain gamma limit, it actually converges to a functional that penalizes curvature. But before let me. I'm sure a lot of you have seen non-local isoperimetric problems before, but let me remind you, we haven't seen them. We haven't really seen them at the conference yet. So I'm looking at energies of the form E omega, where omega is a set in Rn with given mass m. So m is bigger than 0, and so that the perimeter is finite. So if you want, it has finite surface area. And the energies take the form, well, one term is the perimeter. So this would be the isoperimetric part of the non-local isoperimetric problem. And the second part tend to be double integrals over some kernel mod x minus y dy dx. So again, the first term just being the perimeter and us specifying a mass means this behaves a bit like the isoperimetric problem. So the perimeter wants to keep everything together, and even if you haven't seen this one before, it will probably be very intuitive to you that the minimizers, if you just have the perimeter term, are balls. So this guy likes to keep everything together. You can also think of it as resulting from surface tension on a fluid. And the other term is that typically these kernels take map 0 infinity into 0 infinity, and generally they are decreasing. And that means that, well, this term if this term gets small points, a point in omega wants to be 2 points in omega want to be as far away from each other as possible. So this is a repulsive term, and then you get the competition between the attractive perimeter and the repulsive non-local term, and you have all the ingredients you have all the good ingredients for pattern formation. And the obvious questions are, what are the minimizers of this? How do they look like? And because because you have this competition between attraction and repulsion, there is even a question of non-existence. Let me show you this in an example. Namely, first example, Gamow's liquid drop problem. Model, liquid drop model. So what do we have here? Here we take the dimension to be 3 and the kernel to be 1 over r. So that's Coulomb repulsion. Then this is a model for the nuclei of atoms, where you model them as charged liquid drops. The perimeter is a result of surface tension, and Coulomb repulsion, well, is repulsion of charged particles, like charged particles. And what is known about this is the following. I'm going to attribute this theorem to Cyrill and Hans Knüpfer in writing. So this is 2013 and 14. A whole bunch of other people contributed to similar things that I should also mention, but I'm not going to write them down because the list is quite long. And I apologize to the people in the audience who I'm not going to write down now. It's Julien, Figali, Fusco, Maggi, Milo, Morini, Otto, Lou, Frank, Kileb, and now. I apologize. I'm not, I'm not doing slides. And the theorem is that there exist three masses. M0, M1, and M2 that are increasing and bigger than 0. And we have three statements. For M less or equal than M1, minimizers exist. Second, if M is less or equal than M0, then you know that minimizers are balls. So you get the minimizer of this guy despite there still being a repulsive effect. And the third is if the mass is bigger or equal. I should probably put it strictly, doesn't matter. I should put it bigger. If the mass is bigger than the last mass, then you have no minimizers. And especially in this model, that shouldn't be too surprising because we know that sufficiently heavy nuclei of atoms tend to want to split. They're only metal stable, and if you want, if you manage to do that in a controlled way, you can get energy, and if you do it uncontrolled, you get a big boom. But anyway, so that's what's known about this model. And the conjecture is, well, I guess most of you could guess. All masses should be the same, but we don't know. Okay. So that's basically to introduce this class of problems. I'm not going to work on Gamow's liquid drop model itself. I'm going to be interested in slightly different effects, and for that, I'm going to show you a model that Cyrill and I worked on before, which is in 2 dimensions, and the kernel is now given. Essentially, we want to take the kernel 1 to the r cubed. That would be dipolar repulsion, but it turns out that this guy, that the integrals would diverge if I just choose this. So I need to regularize, and I'm just doing a small scale cutoff. So if r is less than some delta, I just set it to 0. I cut out the singularity. And then the energy I look at depends on 2 parameters, lambda and delta. So one is, of course, the perimeter. And then I'm subtracting integral omega complement. So I'll give you the expression in a second. The difference here is a minus and a complement here. If whatever you have here is integrable, you can just add a 0, and then this changes. You just add the You add the complete integral over the space. You change one set to a complement and get a minus, and some additive constant that only depends on the mass, and we don't care. So that explains this, and it's writing it like this will be convenient for us. dy dx. But if I do it like this, I said, well, I had to regularize the kernel because if I didn't have delta to 0, this would diverge. In fact, you can show it diverges logarithmically. So if you want to have anything reasonable in the limit delta to 0, we should counter that. So we put a log here and we put a parameter over here. And then what happens in the limit delta to 0 is that this kernel starts to concentrate on the boundary, and you only get you kind of only see to the leading order. You only really see the boundary of omega. So what we get here, and this is in 19, where, well, we have two things. First, oh, actually, there should be a 4 here. Never mind. That's just a normalization, don't worry about it. It allows me to say if lambda is less than 1, then I can compute the gamma limit of this guy in the L1 topology. And it just converges to the perimeter. Well, not quite. That's the one here is the perimeter term in front. The minus lambda is what's coming from concentration on the boundary. And of course, this can only work for lambda less than 1, because otherwise I don't have anything here, or I even have something negative. And you even get that if lambda is sufficiently big, finite but big, then minimizers are holes, disks.
Sure. Sure.
Delta, yeah, thank you.
You sure?
Well, I'm going to have a different example. In a second, I'm going to look at limit delta lambda to infinity. So that's where that comes from. But yes, of course, as in the limit of in the gamma limit for small but positive delta minimizers are actually still disks. This was also later done in a more general setting by Marc Pégon and co-workers. I think Nelly and Goldman in various combinations and papers. They did it for more general kernels. I think their paper doesn't quite cover our kernel because it's just borderline for them, but they have a very similar result. And I'm going to refer to that in a second. Second thing we could also, well, the very natural question is, well, we know what happens for subcritical lambda. What happens at critical lambda? Critical lambda would be lambda equal 1. And there we need to go to the next order, because, well, the leading order gamma limit is 0. And it's probably not terribly surprising that the next order is actually a logarithm. So if you multiply this guy with the logarithm, then we can compute the gamma limit. We can actually compute the gamma limit. And let me not be too precise here because the formula is a bit long. Basically, this converges to something I would call a non-local curvature functional. Well, in the form we have written it down. It's also a bit similar to a knot energy, funnily enough, but it's not couldn't, we have an expression, we couldn't really do much with it. But what we then asked is, well, the story in Gamow is kind of, the conjecture is, well, minimizers are balls or they don't exist. And that's, I mean, of course, that's physical intuition maybe, but also it's kind of what else would it be? And we asked ourselves, well, maybe in this model, because you have rather we wanted to see whether in this model we could actually have symmetry breaking. So if the model is completely isotropic, but maybe in experiments in which this model applies, you often see so round bubbles, or you see stripes. And the hope was that maybe you can see stripes in this model. We couldn't quite do it. But if we modify the kernel a bit, and I'm not going to write down the modification now, we actually could prove that you have non-spherical minimizers. So we perturb the kernel in an isotropic way, but we still get we still get the existence of non-spherical minimizers. So that's a bit of a warning. Solutions don't need to be isotropic just because your problem is. But in the meantime, so we couldn't say much about the actual minimizers of the gamma limit, but Hans Knüpfer and she were able to prove that if the mass is much less than 1, minimizers are disks. And they use a very different representation of the limit than we saw. But okay. At this point, we said, well, we don't. Somehow the non-local part here makes the problem pretty hard, and also if you in the disks versus stripe debate, it always seemed like somehow the repulsion at infinity was just too strong to really handle. So we asked, well, what happens when you take a model where you actually have much, where the long range repulsion isn't as strong. So we said, well, let's leave that functional. Let's look at something different, and let's look at something that localizes more strongly. And what we ended up taking was the stream Gamow model. And I'm going to write down what I mean for now. So we're still in 2 dimensions for simplicity. And the functional again depends on a bunch of parameters. Alpha is going to be a screening parameter. And I take a lambda bigger than 0. That's going to correspond to the mass in a second. And the functional we look at is f lambda alpha, depending on omega. And, well, parameter, of course, minus, and now lambda squared divided by 8 pi omega complement e to the minus lambda alpha x minus y dy dx. So we didn't have this exponential cutoff up here. I just have Gamow, and but okay, we put in the effect of screening and we get this guy. And we ask ourselves, well, what happens? Okay, I should tell you what lambda is. Lambda, I did a rescaling, so I set the mass to 1, and then lambda squared corresponds to the mass I had over here. So I'm going to take lambda to infinity in a second. That's going to that corresponds to large mass. Okay. Well, similarly as before, well, the kernel is biggest where omega is close to its complement, so it concentrates on the boundary. The lambda squared is actually chosen, you know, if you work it out, the factor lambda squared is chosen so that you actually do get concentration on the boundary, and the result by Merlet and Pégon, this tells you that if alpha is bigger than 1 over square root 4 pi, then the f lambda alpha gamma converges with respect to the R1 topology to 1 minus 1 over 4 pi alpha squared perimeter. Okay. In a certain sense, they already did that for us. Again, if lambda is sufficiently big, you get that minimizers or disks. And they also, they're also that. So instead of looking at the subcritical case, we are free to look at the critical case. And then there is the question of, well, what happens? And, well, what do? You do computation, you plug in a nice set. Say smooth, you don't need smooth, you just need C2, 1, I think, it doesn't matter too much. And you do an expansion of the energy, and you end up that I'm going to use this as an upper bound later, so I'm just going to write an upper bound. You could get a matching lower bound, and well, what you get is not terribly surprising. The parameter with a correct prefactor. But we're really after the next order term, and the next order term is, okay, some number. And the interesting part comes now. You get an integral over the boundary, curvature squared, plus higher order terms. So, well, lambda squared. So the next order should be the elastica functional, integrate curvature squared. And the question was, well, can we prove this? And the answer is yes, we can, but you have to be a bit careful, because if you just take the curvature on its own, well, the curvature doesn't control the perimeter, even if you have mass control. So, for example, if you take the ball of radius r plus 1, and so you look at an annulus, you calculate this, you realize this scales like 1 over r. So you can drive the elastica energy, the elastica functional to 0 with fixed mass, and nothing interesting happens. So if we want to actually see this term and not have to go to yet higher order, we should still keep a bit of the perimeter we have here. And that's the theorem. So we take a sequence lambda to infinity, and we take a sequence alpha n, which converges from above to the critical value, such that the sequence sigma n, defined as lambda n squared 1 minus 1 over 4 pi alpha n squared, converges to some sigma bigger than 0. So this is the prefactor you get if you multiply the energy by lambda squared, and we still want we don't want this to be 0. We want to have a bit of perimeter control in the end. So that's that, and well, then the gamma limit with respect to the L1 topology is precisely what you would expect it to be after this discussion, that is. Well, you keep sigma times the perimeter, and you get pi, pi integral boundary of omega curvature squared dx. The pi you simply get from inserting the critical alpha here. But it's not quite this, because, well, you're looking at an L1 gamma limit. This guy is not lower semi-continuous with respect to the. I mean, it's if you want to write this down, you need a curvature squared. You only take an L1 gamma limit, so it's a question of, well, what does this mean if the boundary isn't nice enough? So what you really should do is you should take a relaxation. That's actually a bit of a subtle issue. I'm going to skim over. I'm only going to say that this has been calculated by Bellettini and Munyai. 2004, I think. And the main problem you have is that in the limit, boundaries might touch, and then you have a problem with, well, if you go through this loop in this orientation, it's not clear whether, what problem is this colliding, and it could happen on, it could happen. These collision points could have a clustering point, and it gets messy. It gets terribly messy. I'm just going to ignore this issue. We have to deal with it, or they have to deal with it. But okay. Now, what's the time? I have 20 minutes. Okay. Right. So, the gamma limit comes without a compactness statement because things might break up and fly away to infinity. For minimizers, this doesn't happen. So I can still get that minimizers converge to minimizers. Well, maybe I should say what the minimizers of the limit are. And also they are already known. This is Goldman, Novaga, Novaga in 2020. So their statement is that there exists a critical sigma bar bigger than 0, so that if sigma is strictly bigger than sigma bar, minimizers are disks. So if you pay enough perimeter, you get disks, and if you don't pay enough perimeter, you don't get disks. You get annuli, so you get a big ball, and then you cut out a small ball. And it doesn't actually matter where you cut out the small ball because the limit is local. So you can shift that around as you wish. So in particular, well, minimizers of our along the sequence, minimizers at some point won't be working.
And when sigma is sigma bar, is either one, right?
If sigma is sigma bar, both can happen. Yeah, it just crosses over.
There's nothing no third alternative.
No. Okay, so that's the statement. Let me give you an idea of how to prove it. I'm of course not going to do the entire proof because, well, we all want to go home today. Or to our respective hotels if we stay longer. So before I go into you know, compactness, upper bound, lower bound, and all of that, I'm going to rewrite the energy. I still have it up there. And what I'm going to do is I'm going to define a function phi, which is just which solves the equation Laplace. Phi equals the potential. A equals the kernel. Lambda alpha r divided by r, and with that I can integrate by parts in the expression up there, and I end up with lambda alpha omega equals, well, I didn't touch the perimeter. I'm not yet touching the prefactor either. But one of the integrals up there is going to turn into an integral over the boundary. The other one I'm keeping. And the expression I get, well, it's not terribly important right now, but let me write it down. E to the minus alpha lambda x minus y alpha lambda x minus y dy h1x the other way around, dx dh1y. Okay, so now let me go into a boundary point. Let me draw a picture and go into a boundary point. Now, say y is here, then I have a tangent plane here, right? Normal, and that's the nu of y. That's the outer unit normal. And what I do is I want to compare the set to the lower half plane that I get up here, and I just, if you want, add and subtract that here, and what I get is that, well, if I compute what the guy on the half plane is, I get precisely our favorite one, our favorite prefactor times the perimeter, and now plus integral over the boundary, and here, so this down here is I take as h minus mu y. I get the half plane symmetric difference to, well, the set. I want to shift the boundary point to 0, and I actually want to blow up. That's convenient on our part, and what you get is 8 pi alpha, I think just alpha. And here you actually get something positive. I shifted, so this is x divided mod x e to the minus alpha x divided by x dx h1. And this looks extremely good, because we already have the correct prefactor for the perimeter. We don't actually have to, in a certain sense here, we don't have to do anything anymore. And down here, well, what we have an integral over the boundary, that's good. And here, we integrate something positive, comparing a blow up of the set with the half plane. So this already looks like, should remind you of curvature. How much does the set deviate from the boundary deviate from its tangent plane? And that's precisely what we're going to exploit for compactness. So, what are we going to do? Let me draw another picture. Okay. Let's say this is y, and I have my half plane here. And say we have a parametrization of the boundary unit length, and I look at a point y plus 1 over lambda. Just look at an increment if you want. And here I also have a half plane. And now, essentially by some triangle inequality, well, here in this point you compare the half plane to the set. Here you compare the set to another half plane. So you might as well compare the two half planes, and you're left with integrating. You're left with integrating this kernel on the symmetric difference of those two half planes. And if you work also here you have a normal. And if you work everything out, you realize that you get lambda squared, and then the difference, y not gamma, of the two normals squared. This is bounded by, well, lambda squared times what I'm going to call now times the inner integral. What I mean is simply this the inner integral here, so the expression that compares the set to the half plane. So that if I integrate this guy now, I get somehow a discrete W12 estimate for the normals. And well, what's the W12 norm of the normals? Is the curve squared. The L2 norm of the curvature. So from this estimate you get compactness. You turn the crank if you know the Frieseke-James-Müller geometric rigidity and plate theory argument. Basically, this is mimicking what they're doing, except that we don't have to deal with the geometric rigidity part. Makes this a lot easier than it is. Anyway. So that's, in a nutshell, that's the idea of compactness. Let me give you similarly quickly an idea of the upper and the lower. Here we essentially also use this representation, except we're going to rewrite the second part a bit. And so I also multiply with lambda squared along the way, because why not? So if I multiply the first part with lambda squared, I just get a sigma n perimeter. Okay, and the second part I rewrite. Here, again, integral of a boundary, and now in the inner integral I change variables. I compare to the half plane belonging to the E2, and so here I need to rotate the set so that its normal becomes E2, and I do an anisotropic scaling. So this is a rotation, so that the picture over there really looks like this. So this is E2 now, and that's the point of the rotation. Here, a lambda is the matrix that maps the first entry to lambda and the second to lambda squared. What this does is that that's the scaling that if you blow it up like this, your sets converge to a parabola. And this is still E2. Or rather, the boundary converges to the parabola that maps x1, and the first component is x1. Second component, up to a sign that I don't worry about, is the curvature halves x1 squared. I do the scaling where you see the curvature. Oh, I should. Okay, sorry. dx dh1 y. And so the question essentially becomes, well, what happens with this integral when your boundary converges to a parabola? So here you integrate. So in the limit you expect to integrate over the parabola over the say something like this: x1 up to symmetry 1 squared less than or equal than x2 less or equal than 0. You integrate the kernel. The kernel is x2 times e to the minus alpha. I keep, and well, here I have x1 squared, and I have a 1 over x2 squared plus x2 squared divided by lambda squared. Lambda goes to infinity, so you can hope that you just get x mod x1 here, and also down here you get x1, only get x1 squared, and that's the x. And now, well, you need to integrate all these sets, right? First you integrate in x2 direction, and you integrate in x2 direction, you get one factor of kappa from the length of the interval, you get another factor from the fact that you integrate x2. and the rest is an integration you can carry out. So this is some constant that depends on alpha n times curvature squared. And that's how if you want in an upper bound, a very quick argument in an upper bound, you get the curvature squared out. Turns out you can also follow this calculation and the strategy for the lower bound, except that you need to make it work if you have a sequence of sets here. Crucial is, of course, that the L2 norm is weakly lower semi-continuous, but you know, if you want to make everything work here, also with the geometry, you have to invest a bit of measure theory. I'm not going to do that now. Instead, I will finish my talk and thank you for your attention.